So the third thing that we need to look at is the fact that the dot product is distributive over vector addition. So if we now take a third vector, which we'll call the vector c, and we consider how we could work out this thing here, which is the dot product of a with the vector that you get if you add the vector b and c together, the claim is that this is equal to what you get if you dot product a with b and you add that to the dot product of a with c. So on the picture here we have the vector a, here we have the vector b, we're adding on the vector c to get this new vector b plus c, and we're trying now to dot product the vector a with the vector b plus c, and the claim is that we can just dot product a with b and a with c and add those two answers together. So we want to understand why this is true. So let's begin by splitting both vector b and vector c into components, a component that's in the same direction as the vector a and a component that's perpendicular to the vector a. So in red here we have it for vector b. So this is the component of vector b that is in the same direction as vector a, and here is a component that's perpendicular to vector a. And then we can do the same for vector c. So we have a component that's in the same direction as vector a, and we have a component that's perpendicular to vector a. Now, when you consider the vector b plus vector c, the new component that you're going to get here in blue that is in the same direction as a, the claim is that's going to be equal to this in red, the component of vector b that's in the direction of a, plus the component of vector c that's in the same direction as a. And the reason that that is true is that when you add the vector b to the vector c, it's the same thing as adding all the components together. So it's the same thing as adding this vector with this vector, which obviously forms the vector b, and then add on this vector and this vector. Those two green vectors make the vector c. So if you add all those four, the two reds and the two greens together, you'll then get the answer to the vector b plus c. Now, of course, that addition, that four-part addition, consists of two parts that are in the same direction as the vector a, and then two parts that are completely perpendicular to the vector a. Now, when you add those two parts that are completely perpendicular to the vector a, they will give another vector that is completely perpendicular to vector a. So, you can therefore see the vector b plus c as being the addition of these two parts that are in the same direction as vector a, plus the addition of the two parts that are perpendicular to the vector a. And then if we want to consider what the component of b plus c in the direction of vector a is, all we need to do is look at the addition of these two components that were in the direction of vector a. We don't need to consider the two components that were perpendicular, because the resultant of adding those two together will still be perpendicular completely to vector a. So if we want to now work out what the dot product of a with b plus c is equal to, then we need to take the length of vector a and we need to multiply it by the length of the component of b plus c that's in the direction of a. But we've just agreed that that is equal to the length of the component of vector b that is in the direction of a plus the length of the component of vector c that is in the direction of a. Now, we can write the length of the component of vector b that is in the direction of a as the dot product of a with b divided by the length of vector a, and that's because the dot product of a with b is just the length of vector a times the length of the component of vector b in the direction of vector a. So if we divide both sides by the length of vector a to bring this down here, then we get that this thing is just going to equal the length of the component of vector b that's in the direction of a. Similarly, the same is going to be true for the length of the component of vector c that's in the direction of a. It's just going to equal the dot product of a with c divided by the modulus of a. And then if you just cancel the modulus of a here, you can see that then the dot product of a with b plus c is going to equal the dot product of a with b plus the dot product of a with c. And this works even in the case that one of the vectors has a negative component in the direction of vector a. So in the picture we've got here, this is a more complicated example. So here we have the vector a, here we have the vector b, and here we have the vector c, and we're still considering the same question of what is the dot product of A with the resultant vector that you get from adding b to c. This time it's complicated by the fact that you can see this vector c here, its component in the direction of vector A is actually anti-parallel to A, pointing in exactly the opposite direction to the vector A. So again, b plus c is all of these separate vectors added together. Now we don't care about the two parts that are perpendicular to A, because when they're added together, they're still going to give a vector that is completely perpendicular to A. So the component of b plus c that is in the direction of vector A is going to come from this bit being added to this bit. So if we want to work out what the length of the component of b plus c that is in the direction of vector A is equal to, we need the length of this one, and we need to subtract away the length of this one here. So the dot product of A with b plus c is going to equal the length of vector A times the length of the component of b plus c that is in the direction of vector A. But we've agreed that that is going to be equal to the length of the component of vector b that is in the direction of A, subtract off the length of this line here, which is the component of vector c that is in the direction of vector A. Now, we know from what we've discussed previously that the length of the component of vector b that is in the direction of vector A is going to be equal to this. The dot product of A would be divided by the length of vector A. Now, I've added in this bit here, and I want to convince you that this is right. We wanted negative of the length of this line. When you dot product A with C and divide it by the length of vector A, that is going to give us the length of the component of vector C in the direction of vector A. But remember, the dot product when the component is anti-parallel to the initial vector, vector A, is going to be negative anyway. So this number is actually going to be negative because this is going to come out negative. So if you dot product the vector A with the vector C, it's going to be equal to the length of vector A times the length of the component of vector C in the direction of vector A, but because it's anti-parallel in this case, it's going to be the negative of that. So this is going to already have that negative number there. So this is going to be the length of this line, subtract the length of this line. And then we just cancel off the length of A here to get that the dot product of A with B plus C is equal to the dot product of A with B plus the dot product of A with C. So this formula works, this distributive law works. The dot product is distributive over vector addition.